Okay, so picture this. You're a developer, maybe just an AI enthusiast, and for the last, 5 years, there's been one golden rule.
Oh, yeah. It's written on the wall in permanent marker. The Kaplan scaling laws.
The bigger is better doctrine. Exactly. It's this brute force mentality. You want better poetry from your AI.
At 100 billion parameters.
You want it to solve calculus, build a data center the size of a small city. I mean, it feels like we've been trying to reach the moon by just building a taller and taller ladder.
That's a really good analogy. And frankly, it's hitting a wall. We're running out of data, we're running out of power, and these models are becoming these, unwieldy giants that only 3 or 4 companies on Earth can afford to run.
But today we're talking about a project that might just knock that ladder over. We are doing a deep dive into Aro,
Named after the Ouroboros.
the ancient symbol of the snake eating its own tail, which I admit sounds a little gruesome for a tech deep dive, but conceptually it is perfect. We're talking about recursion.
Looped language models, or LoopELM for short.
And this is a project that just fundamentally challenges that whole status quo. It's asking, what if we don't need more layers?
Right, we don't need to stack the building higher, we just need to use the floors we already have smarter.
It's what they're calling the third pathway.
That's the one.
Yep.
Historically, we've had 2 ways to scale. You add more data, or you'd add more parameters. RO introduces a third axis, loop depth, or, time.
So instead of a brain that's just infinitely wide, it's a brain that actually takes a second to think.
Precisely. And the results they're getting with this are honestly confusing if you stick to the old rules.
Mm-hmm.
We're looking at the RO family of models, specifically a 1.4 billion and a 2.6 billion parameter model.
And just to set the stage for everyone listening, in today's AI world, 2.6 billion is. It's tiny. That's something you could almost run on a high-end laptop. It's not supposed to be a GPT-4 competitor.
It should be a Tor model, but it is absolutely not. The RO team found that their 2.6 billion parameter model is matching, and in a lot of cases, beating standard models that are 8, 10, even 12 billion parameters.
And we're talking about heavy hitters here, right? Like Qwen, Gemma, Llama 3.
Correct. So you're looking at, a 2x to 3x gain in parameter efficiency. It is punching way, way above its weight class.
Okay, we have to unpack this because that sounds like, it sounds like magic. If parameters are the brain cells of the AI, how is the one with fewer brain cells outsmarting the one with 3 times as many? What are the mechanics here?
To get RO, you have to picture how a standard large language model, a transformer, actually works. Think of a car assembly line.
Okay, classic analogy, I'm with you.
You've got station 1, station 2, all the way down to maybe station 100. The car chassis, that's your data, moves down the line. At station 1, someone bolts on a door. At station 2, someone else paints it. It's totally linear.
Right, and once it's past station 1, it never goes back. It's a straight shot, start to finish, and every station has a different person with different tools.
Exactly. That's a feed-forward network. The intelligence, the weights at layer 1 are totally separate from the weights at layer 100. But RO just blows up that assembly line.
Okay, so what do they replace it with?
A workshop. Imagine instead of 100 different stations, you have a small room with just a few extremely expert mechanics. The car comes in, they work on it. Then, instead of shipping it out, they step back, look at their work, and say,
Is this done?
Is this done? No, I think we can refine it. And they go back to work on the same car.
Using the same tools.
The same tools, the same brain cells. They feed the output of their work right back into the input of their own process. That's the recursion. That's the loop.
So the technical term here is shared parameter recursion.
That's it. They're reusing the same weights for multiple cycles.
But wait a second. If I have to loop the model 5 times, isn't that just as slow as having a model that's 5 times bigger? I mean, if the mechanics have to work on the car 5 times, it takes 5 times as long. Where's the efficiency gain?
That is the million-dollar question. And the answer is something they call dynamic computation.
Dynamic computation.
Yeah.
Okay.
Think about the assembly line again, the standard model. If you ask it, what's 2 plus 2? That simple question has to travel through all 100 stations.
It takes the same amount of compute to answer a toddler's math question as it does to write a dissertation on quantum physics.
Which is...
incredibly wasteful, yeah.
It is. It's static.
Yeah.
But RO has an exit gate.
An exit gate?
After every single loop, every cycle in the workshop, the model does a quick check. It looks at the state of the answer, and it calculates a confidence score. If the question is, what's 2 plus 2? After just one loop, the model goes, I got this, it's 4, I'm confident.
And it exits, it kicks the car out of the workshop early.
Exactly. But if the question is, I don't know, explain the geopolitical nuances of the 19th century. He goes, whoa, okay, this is complicated. Let's run it through again. And it stays for 4, 5, maybe even 8 loops.
So it decouples the size of the model from the depth of the thinking.
Yes, that's the key. It separates compute depth from model size.
That feels like the holy grail for deployment, because right now, if I want smart AI on my phone, I can't really have it. My phone battery would die in 10 minutes trying to run a 70 billion parameter model.
Right. But with LoopELM, you could have a small model, that 2.6 billion one, that just sits there using very little power for simple tasks. But when you need it to do some heavy lifting, it spins up the loops.
And it gives you 12 billion parameter performance on a 2 billion parameter chip. Just by taking a little more time, it trades time for space.
That is the fundamental shift.
Okay, but I want to push back on this a little bit, because there has to be a limit, doesn't there? You can't just loop your way to omniscience. If I have a tiny, tiny model, say 1 billion parameters, and I let it loop for 1,000 years, it's not going to suddenly know the capital of a country it's never heard of.
That is such a crucial distinction. And the RO team actually ran a specific set of experiments to test exactly this. They call it the physics of language models.
I love that. Physics of LMs, like they're testing the laws of gravity for intelligence or something.
They wanted to distinguish between two things, knowledge capacity and knowledge manipulation.
Okay, so storage versus processing.
Exactly. So they made these synthetic tasks. One was called capo, pure memorization. They fed the models fake biographies, random names, birth dates, universities, just raw, disconnected facts.
And then they looped it to see if it remembered better.
Yep. And the result? A flat line.
Zero gain.
Absolute zero. It turns out there seems to be a hard physical limit to how much information a neural network can store. It's about 2 bits of knowledge per parameter.
So it doesn't matter how many times you loop or how hard you think. If the fact isn't on the hard drive, you can't access it.
Exactly. My analogy holds up. Thinking harder doesn't help me remember a phone number I never learned.
Right, but then they looked at the other task, the mano task, and the reasoning benchmarks.
The processing tasks.
Right.
Logic puzzles, elementary math, spotting logical fallacies. Things where you have the information, but you have to figure out how to use it. The graph just shoots straight up. We're talking massive gains. On tasks like formal logic or elementary math, the oral models showed 120, even 150% improvement over the baseline models. 150%, just by letting it loop. Just by letting it think. It basically proves their hypothesis. Parameter count dictates how much you know. That's your library size. But loop depth dictates how well you can think about what you know.
It's the difference between having a massive library with a lazy librarian versus a small library with, I don't know, Einstein working the desk.
That is the perfect metaphor. The standard huge models are these giant libraries, but the librarian is just rushing to grab a book and get out. RO is a smaller collection, but the librarian sits down, reads the book, cross-references it, and then gives you a synthesized answer.
And this idea of synthesizing or thinking, it brings us to what I think is maybe the most important part of this whole thing. We need to talk about reasoning. Because usually, when we want an AI to solve a hard problem, we use chain of thought, right? We tell it, think step by step. And the AI writes out, first I'll do X, then I'll do Y.
Right. And for a long time, we all just assumed that was it actually thinking.
But this Arrow paper, it throws some serious shade at standard chain of thought, they call it. What was the phrase? Post hoc rationalization.
Yeah, this is kind of a dirty secret in AI research. Often when a standard model outputs that step-by-step text, it isn't actually using those steps to find the answer. It often decides the answer instantly in the first split second, and then generates the reasoning text afterwards to justify the decision it already made.
So it's faking it. It's just making up its work after the fact.
It's like a student who writes down the answer to a math problem first and then scribbles some fake working out steps backwards to make the teacher happy.
That's concerning, because if the reasoning is fake, we can't trust it.
Exactly. It's not faithful. But Arrow is different. Arrow uses latent reasoning.
Latent meaning hidden.
Yes. In Arrow, the thinking doesn't happen in the text output. It happens in the hidden states, the mathematical vectors inside the model, between the loops.
So it's thinking silently before it even speaks.
It is manipulating concepts in a pure, abstract mathematical space. And because it's doing this before it generates the final answer, the reasoning is causal. It leads to the answer. It doesn't just justify it.
But how can they prove that? I mean, how do we know it's not just stalling for time in the loops?
They ran this brilliant experiment using the Quora question pairs dataset. They took ambiguous questions, tricky ones where the answer isn't obvious, and they monitored the model's internal prediction at each and every loop.
Like peeking into its brain while it's thinking.
Exactly. And they found that in the early loops, say loop 1 or loop 2, the model might be leaning toward yes. Its internal state is predicting yes. But then it loops again. It reevaluates. And by loop 4, it flips its prediction to no.
It changed its mind.
It changed its mind. That is the smoking gun. If it were just post hoc rationalization, the answer would be locked in from the very start. The fact that it flips means the loops are doing actual cognitive work. It's refining its understanding, spotting its own errors, and correcting them.
That is wildly cool. It feels more, well, more human. It's that moment of saying, wait, let me think about that. Actually, no, you know what? That's wrong. Here's the real answer.
It creates a faithful reasoning trace, and this internal refinement has this huge side effect that goes beyond just getting math questions right. It makes the model safer.
Okay, safety. This is the hex PHI benchmark part of the paper.
Yep. They found a really strong correlation. As you increase the number of loops, the safety scores go up. The model becomes significantly less harmful.
Why, though? Is it just too busy thinking to be mean?
Not exactly. Think about how jailbreaks usually work. You know, when people try to trick an AI into writing malware or hate speech, they usually rely on speed and confusion. They try to trigger a knee-jerk reaction.
Role play as a villain or ignore all previous instructions, that kind of thing.
Right. They try to bypass the safety filter before the model even realizes what's happening. But when the model loops, it creates this thinking buffer. It has more computational depth to evaluate the prompt. They actually visualize this using PCA analysis.
A map of the model's brain. What did it look like?
At loop 1, the harmful prompts and the benign prompts were all mixed together in this one big, messy cloud. The model couldn't really tell them apart.
It was confused.
Totally. But by loop 4, and especially by loop 8, those clusters separated beautifully. The model effectively sorted them. It was able to say, wait a minute, I see the pattern here. This is a harmful request.
Yeah.
And then it refused it.
You just mentioned loop 8.
Yeah.
I thought Aro was trained on 4 loops.
This is the wildest part of the research. It's called extrapolation. They train the model to think for 4 cycles. That's all it knows. But then at test time, they forced it to keep thinking. They essentially held the door shut and said, don't answer yet, give me 8 loops.
And it didn't just break.
For safety, it got better. The safety score kept climbing. It suggests that intent recognition, understanding what a user really wants, is a process that benefits from almost infinite recursion.
That is fascinating. So if we just let an AI think for 10 minutes, it becomes a saint?
Well, there is a trade-off. They found that while safety improves with extrapolation, raw performance on, say, math problems tends to peak at the trained depth, so loop 4. If you force it to loop to 8 or 10 on a math problem, it starts to overthink it.
It second guesses itself.
It starts to drift. The reasoning becomes disconnected. So you can't just loop forever for everything.
So how does the model know when to stop? If it can exit early or stay late, how does it manage its own time?
They use a training technique called entropy regularization.
That sounds like a sci-fi weapon. What does it do?
It's basically a way to prevent the model from being lazy. Without it, the model might just try to exit at loop 1 for everything to save energy, or it might loop endlessly. This forces it to explore different depths, to learn that some problems need 1 loop and some need 4.
It teaches it time management. It teaches it to assess the difficulty of a problem on its own.
Exactly. An unbiased exploration of depth.
It feels like such a massive shift. We aren't just building bigger bulldozers anymore. We're building skilled architects who know when to sketch and when to build.
That's the shift from scale to substance. For years, the only metrics that mattered were how big is your data set? How many parameters do you have? Now, Aro has firmly planted a flag for a third metric. How deep is your loop?
It really challenged that scarcity mindset, too. You hear all this doom and gloom about running out of data to train on, that the internet is only so big.
Right. Data scarcity is the big looming wall for AI scaling. But LoopLM suggests we don't necessarily need more text. We need to squeeze more reasoning out of the text we already have. We need to, chew our food more thoroughly.
I love that image, chewing the data. It changes the economics of AI, doesn't it?
Completely. If you can get 12 billion parameter performance out of a 2.6 billion parameter model, suddenly the hardware requirements just drop to the floor.
That democratizes the whole technology. It moves it from the server farm to the edge device to your phone.
And it opens up that third pathway for research. We might see a future where the smartest models aren't the ones with the most connections, but the ones with the most sophisticated internal recursion.
It makes me wonder about the user experience of the future. Right now, we expect AI to be instant. You hit enter, the text streams back, it's almost frantic.
Speed has been the metric, yeah.
But if Auro proves that thinking time creates better, safer, more faithful answers,
We might just have to get used to the pause.
the awkward silence.
Maybe it won't be awkward, though. I mean, think about human interaction. If you ask a supposed expert an incredibly complex question and they snap an answer back in a millisecond, do you trust them?
Probably not. It sounds rehearsed. Canned.
Exactly. But if they sit back and they look at the ceiling and they purse their lips and think for 10 seconds, you trust that answer more. The pause implies depth.
Auro is the architectural equivalent of that pause.
It's the move away from predicting the next word to predicting the next thought.
And that leads me to my final thought for everyone listening today. We spend so much time in our own lives maximizing our throughput.
Right.
Reading more books, listening to more podcasts at 2x speeds, scrolling more feeds. We're all trying to increase our parameters.
We're trying to maximize our capacity.
Exactly. But Auro teaches us that capacity is capped. You can only memorize so much. The real gains, the 150% improvements, they come from the loop, from the recursion, from taking the information you already have and running it through your own mental processor one more time.
It's not just about what you know. It's about how many times you review what you know.
So next time you're facing a complex problem, don't just reach for Google. Don't just reach for more data. Be like Auro. Close the exit gate, stay in the loop, and think it through one more time.
Quality over quantity. Always.
That's a wrap for this deep dive. We'll catch you in the next loop.
Goodbye, everyone.